Assalamualaikum and hello everyone. We will from group 2 will be review on heavy metal contamination in China mining area. Okay, firstly I will introduce myself. My name is NURUL NADIRAH. First I will talk about contents for today. Content for today is a source of heavy metals, and case study that been reviewed is Northwest China and Guangxi province. China is one of the largest global producer and consumer of metal such as iron, lead, tin, manganese, zinc, arsenate, copper, nickel, mercury, and so on. One of the environmental pollution that involve is a heavy metal pollution or soil pollution. Okay, the numbers of study that been reviewed show that the highest level of heavy metal exposure in is frequency that causes of permanent development disabilities, so that the soil pollution of heavy metal has been a major issue in China. Okay, what is the heavy metal? Heavy metal is a metal treatment that has high density and toxic in the low concentration. The common heavy metal that been studied is lead, copper, mercury, nickel, iron, and so on. Okay, the heavy metal can lead to the soil pollution. Okay, for the sources of heavy metal, um, the sources of heavy metal contaminant that been measured is mining activities. Heavy metal may occur in soil by addition contribution from the agriculture, urbanization, and mining can also lead to the heavy metal pollution. Okay, the heavy metal concentration in the soil, which is a cover with the mines tilings, had a great surpass the minimum allowable concentration level of Chinese soil guideline, which means as if the concentration of heavy metal concentration from the mining is higher, so the soil will be polluted and contaminated. This will cause several problems for the surrounding area.
Hi, my name is NAJWA and I will continue about the case study for number 1, which is in North area mining activities. The location for the mining activities at the Chendong coal mining, which is at the Chendong. There are several mine activities, but for this case study, it's only took three sample location, which is at the Delyota, Bulianta, and Ujialiang coal mine. So the heavy metal that consists in the coal, which it consists of lead, mercury, nickel, tin, cadmium, antimony, and arsenic. Okay, for the soil behavior, soil characteristic, and the reaction, it have three criteria that we have to look, which is the physical, chemical, and biological quality of soil. But for this study, it's only focused on the soil physical quantity and the soil moisture and groundwater table. So in the soil physical quantity, they have soil cohesion, internal friction angle, soil organic matter, bulk density, dry density, porosity of soil, and soil water content. For the soil cohesion and internal friction angle, the consolidated shear test were performed to get the result, which is the result are get before the mining activities. The soil cohesion are increased then after the mining activities, which is while the internal friction angle before mining activities are lower than after the mining activities, which is before mining. For internal friction angle, it gets 28.9, and after mining activities, the value for internal friction angle is 31.1. To get the result of soil organic matter, the potassium dichromate colorimetric method and physical index was performed, which is its same result with the soil cohesion. Before mining, it has increased organic matter, but after mining, the soil organic matter was decreasing. The last one, the testing were performed to determine the soil physical quality for bulk density, dry density, and porosity, also soil water content. The oven drying method was performed. Only the soil water content have the result, which is same before this. Before mining, the result was shown increasing in water content, but after mining, the result are shown decreasing. This table of result can getting in the report or in the article that we write. But for the bulk density, dry density, and porosity, the results are shown. There is no so obvious value changes. And lastly, for my part, is about soil moisture and groundwater table. So, to monitor the groundwater table, the method that they use is remote sensing and GPR method. So, in soil moisture, the result shown there is no influence on soil moisture in the Chendong coal mining area. Before and after mining, the result showing that soil moisture are not influenced into the soil. But for the groundwater, according to the water well data, groundwater table decreasing roughly 8.4 meter following the mining, and even after 2 years after mining, the groundwater table was remain 7.3 meter lower than primary water table before mining activities. And the GPR data reveal that extensive water well pumping rather than stratum movement and cracking is the primary driver of groundwater table reduction. So it's well said that well pumping activities affect the groundwater table. That's all for me. Thank you.
Assalamualaikum, my name is HANISAH. I would like to present about the manganese mining at Guangxi province, China. There are 3 things that I want to present, which are heavy metal concentration, standard methods, and soil characteristics and behavior. Okay, for heavy metal concentration, there are 4 types of heavy metal in manganese mining, which are manganese, cadmium, zinc, and chromium. There are 5 types of standard methods that are used to detect the physical-chemical condition of soils, which are barium acetate methods for cation exchange capacity (CEC), and standard methods of Soil Science Society of China for total nitrogen and total phosphorus, and 1:2.5 soil to water ratio for pH, Walkley and Black procedure for organic matters, and hydrometer methods for soil texture. For table 2, it shows the physical chemicals of soil before and after mining at Guangxi, China. There are 7 samples that took out from different places to be tested. The first is the local unmined land that act as a control. Second is mine drainage, area dominated by Polygonum perfoliatum and Teres vittata. Third is the bare mining area without vegetation. Fourth is an abandoned mineland dominated by Polygonum pubescens and Solanum nigrum. Fifth is the tailing dam with few herbs. Sixth is the abandoned mineland dominated by Erigeron, Acer, and Paspalum orbiculae. And 7 is the unabandoned mineland dominated by Cumerovia strata and glycine soja. For table 3, it shows the classification standard of total nitrogen, total phosphorus, organic matters, pH, and cation exchange capacity. The pH value, the CEC, the total nitrogen, total phosphorus, organic matters, and carbon nitrogen ratio from the tailing dam with few herbs, which is S4, are lower than the other sample. It indicates the nutrient retention of S4 was weak while the other 6 soils are moderate. The organic matters were also relatively similar in the different soil, falling within the range moderate to abundant. However, the sample S4 contained low level of organic matters and it was classified as an OM deficient soil. To be concluded, the manganese mining and the coal mining are reviewed as a source of heavy metal, for example, manganese, cadmium, chromium, zinc, and etc. For coal mining, the soil water content, organic matters, and soil cohesiveness after mining are lower compared to before mining. However, the internal fraction angle after mining are higher than before mining. Meanwhile, for the manganese mining, it shows the increasing of pH value and carbon nitrogen ratio after mining, but organic matters, total nitrogen, and total phosphorus of soil were decreased. That's all from us. Thank you.